Hello. In this video, we will be looking at complex circuit practice dos. All right, so determine the electric potential and the current at each point labeled and consider the negative terminal of the battery to have zero potential. All right. So if we follow our techniques that we know and love, we're going to throw some color onto this circuit. Let's make this a little bit wider. And say, and they even tell us right before the battery, 0 volts. So it should make this 100 volts. So I've already found electric potential at A and D. At D it's 0, at A it's 100. Got to find the rest of these. So I'll start by, I got to figure out how much does it change from A to B. How much does it change going over this resistor? I need to know the current through the resistor. At this point we should be pretty comfortable. Oh, I shouldn't use green because I used green over there. Oh well. We should be pretty comfortable. Oh, that's just ugly. Sorry. Let's use a dark green. There we go. What was I saying? We should be comfortable finding the current in a circuit. In this case, we have a series circuit, so we can do equivalent resistance. You can say these three, they're in series, so together it's like 15 plus 25 plus 10. It's a resistance of 50. So I can pretend this is 50, this is 100. Well, that means a current, Ohm's law, delta V equals IR. This is going to be a current of 2, because 100 divided by 50, 2 amps. Great. So knowing that, and we could have made a table for all these resistors to help us out here. I'm going to skip that for this one, but we'll probably do it for later ones. The delta V of the 15 ohm resistor, 2 amps, 15 ohms, 30 volts. The 25, 50 volts. The 10, 20 volts. So you can see as I go along here, I'm at 100, I lose 30, 70, lose another 50, 20, 20, lose 20, back to 0. Good, it worked out. All right, so the current, I guess we'll make a table of the answer. People are just looking for that. A, B, C, D. The voltage at the point and the current. These are all 2 amps, 2 amps, 2 amps. We had 100, went down to 70, went down to 20, and at the terminal of the battery, 0. Great. So different kind of table, but useful. All right, here we have a parallel circuit. So for the battery is 0. So I can see immediately, if I wanted to, let's just make that table. We have A, B, C, D, E, F, G. Oh boy. I'm just going to write it out. So J, I, H, G, and F, they all have a potential of 0. There's no resistors in between those points, so there's nothing changing the energy. So they all have the same energy. So J, I, H, G, and F, 0 volts. Likewise, all these points, is that 42 volt battery? So that's A, B, C, D, E. A, B, C, D, E. 100 volts. Nope, not 142, my bad. 42 volts there. Okay, so that part's easy. Now let's think about current. I'm told each of these resistors is 4 ohms. I know the delta V for each one. They're going from 42 to 0. I got Ohm's law. Ohm's law tells me delta V equals IR. So 42 over 4. That's not a nice number. What was I thinking? Equals, let's see, 4 times 8 is 32. 4 times 9 is 36. 4 times 10 is, what am I doing with my life right now? 4 times 10 is 40. And then 0.5 to get us that 2 amps. All right, so that means that through each of these resistors, I'm getting 10.5 amps because they're all the same kind of resistor. They're all dropping the voltage the same amount. So B and I have the same current, C and H have the same, D and G have the same because they're in the same loop. And then we just found for all of them equal resistors in parallel, same current. So B, C, D, E, B, C, D, E, I, H, G, F have 10.5 amps. Now A and J are different because that was going down each line here. Well, A has to provide the current from the battery, which is the same for A and J, so we know they're going to have the same current. It has to provide enough that I get 10 down each of these. So it has to provide 4 times what's going down each one. So 10.5 times 4, that's kind of funny. I get for A and J, I get 42 amps. Another way I could have solved this problem is I could have found the equivalent resistance for all these. That would be 1/4, because it's 4 ohms, 1/4 plus 1/4 plus 1/4 plus 1/4. Well, that's 4/4. So 1 over the equivalent equals 4/4. Flip that, 4/4 flipped is also 4/4. So the equivalent resistance of all of this is 1 ohm. 1 ohm and 42 volts, so that's a current of 42 amps. So 42 divided by 1 is still 42. So that would have also given me that the current for each of these is 42 amps, and then I could say, okay, well, it splits into 4. 42 divided by 4 paths. That would also get me this 10.5. So all our rules all lead us to the same place. Okay, next. We have a complex circuit here. It's a combination of parallel and series resistors. So let's see how that affects our answers. 0 volts before the battery, as we're told to do, 9 volts therefore after. So D and C are going to have a potential of 0 volts. A is going to have a potential of 9 volts. Let's make a table for this. A, B, C, D. Current. All right. So A, we just said, and again, this is a different kind of table. This is not the kind of table we were making in previous practices for each resistor. This is just for these points. 9 volts. D and C are 0 volts. B, we don't know. We don't know purple. So we got to find some currents and things to help us do that. And I say, where can I find the current? Well, I don't know this voltage change, so I can't find the current with this resistor. I don't know this voltage change, so I can't find the currents through these resistors. I do know the change of the battery though. So if I make these an equivalent resistor, I can then find its current. So I want to stick together. What can I stick together first? These are in parallel. So I can take this, I can turn it into 1 over 1 plus 1 over 3 is 4/3. I did not make the math easy on this, did I? Then I flip it. So I get Req equals 3/4 ohms. So now I have this guy where this is still 0.5 ohms. And these together are now 0.75 ohms. And my battery is still a 9-volt battery. Put our colors. The combined resistor here we can see is still going from purple to red as the initial ones did. All right, now these are in series. So overall my current 9 volts divided by 0.5 plus 0.75 is 1.25 ohms. Does that come out to a nice number? Nine divided by 1.25. It doesn't. 7.2. amps. Well, we gotta get used to not perfect numbers at some point. All right, so now I can go back. I can say I've got 7.2 amps running through my battery here. So that means the current through A and the current through D are both 7.2 amps. If I was doing this, I wouldn't actually do this table till the end. I would just solve this circuit like I normally would, making myself a table maybe for all these resistors, and then go back at the end and write this table in. So how does that help me? Well, 7.2 amps, 0.5 ohms. I could see this if I was making a table. That's going to change the voltage by 3.6 volts. R times I. All right, 3.6, 9 minus 3.6. That means my purple area over here is 5.4 volts. Add that to my thing. 5.4 volts. Cool. Well, now, again, if I had my other table going, I could say each of these resistors has a delta V of 5.4. It's going from 5.4 back to 0. And then I could find the current through each one. 5.4 divided by 3 is 1.8. So I could say I have 1.8 going down this way. 5.4 divided by 1 is 5.4. And I can check, these should add up to this, 5.4 divided by 1.8, 7.2, good. So let's write those again down here, especially if you couldn't read my handwriting there. So that's the current through B, is 1.8. That's what's going through this resistor. C, it's on the same path as this resistor, so it's getting the 5.4. 5.4 amps, 1.8 amps. All right, D. Almost through these. This is quite the long assignment here. Add some colors. Boom. Label what we know. 10 volts, 0 volts. So A has a voltage of 10. E and D have a voltage of 0. Oh, we got another color in there. Great. And we have a current. It's coming from the battery. And it's splitting to go down these two paths. So it looks like to figure out anything here, I'm going to need to figure out some currents, which means I'm going to need to know this one. Because to figure out purple, I need to know what's happening over this resistor, which is the total current. So let's start shoving things together. These are in series, one loop. So I can add these, that's 20. This one's also 20, so that's combinable. So we got this, we still have the 30. I guess we'll draw this step in. So we have 30, 20, and 20. Combine those two 20s, 1 over 20 plus 1 over 20. Is 2 over 20. Flip that. 20 over 2 is 10. And I can do that quickly. Even I can say, well, 2 of the same resistor in parallel is like half the resistance because I've doubled the number of paths by adding one of those. 30. Battery is 10 volts. All right, 10 volt battery. Overall resistance of 40. 10 volts, 40 ohms, 0.25 amps. So you can go back to our thing here, 0.25 amps. All right, and again, I would suggest you make a table of all the resistors to keep yourself organized, especially if you're not doing all this color stuff. So, oops, 0.25 amps going through 30 ohms. 30 times a quarter is 7.5 for its delta V. 7.5 volts. Start with 10, lost 7.5, have 2.5 remaining. Nice. How does that help me? Well, I can't do anything over here. Well, I could, sort of. I don't know. C. It's easier to go here. 2.5 to 0. Delta V. Oops. Equals IR. We've got 2.5 volts, because that's the change, 2.5 to 0, over 20 ohms. 2.5 over 20 is not a very pretty current. 0.125 amps. All right. 0.125 amps. Now I have two options. I could, since I don't know this, I could combine these two. That'd be 20. And then I would have, if they're combined, then I'm going from 2.5 to 0. And I would find then that the current is 0.125 as well. Another way I could do it, and I knew that because I knew when I did this that they end up being the same. So if this is getting 0.125, this one needs to get 0.125. Or I could say, well, after finding this one, I know at this point, this junction here, 0.25 is splitting into 0.125. So this has to also be 0.125 to conserve current. These need to add up to this. All right, so knowing this, 0.125, 15 ohms, 0.125 times 15, 1.875. So this guy is changing the potential by 1.875 volts. So if I had 2.5, I lost 1.875. 2.5 minus 1.875, 0.625 in this green volts. And I can check that by saying, okay, 5 times 0.125, that should also be this value. 5 times 0.125, 0.625. So I did it right because this is dropping the correct amount of voltage. Alrighty, we are now moving on to some situations where don't know one of the resistors, but we've given some other information about the circuit to help us out. So first one we got here, we don't know this top resistor, but we are told about a current. We're told the current here is 2 amps. And since this is one loop, a series circuit, the current throughout it is 2 amps. So I'm going to use the table method to help us out on these questions. So I'm just going to call this one resistor 1, resistor 2, and resistor 3. So let's fill this table out. We got Ri delta V. Seven ohms, 10 ohms, got a battery, 50 volts, and we're given that the current through each of these is 2 amps. And they all have 2 amps because it's one loop, they're all in series together. Now, you could just look at this. Another way to do this is with the idea of equivalent resistance and say, well, 50 volt battery, 2 amp current, that means overall, according to Ohm's law, the equivalent resistance of this circuit has to be 25 ohms. And so, okay, 25 ohms, 10, 7, this needs to be 8. And you could definitely do it that way, but this is the more conservative approach, you could say. All right, so I drew my table. I drew what I knew. And looking at my table, I can see in 2 of these columns, I know both the resistance and the current for these 2 resistors. So I can find this has a delta V of 14 volts. This has a delta V of 20 volts. So thinking about voltage, I'm gonna throw some colors on my circuit here. All right, 0 volts, 50 volt battery adds 50 volts of potential to my circuit. Don't know anything about R, so I can't really do anything there. We found that this 10 ohm resistor, 10 ohm, 2 amps, we found it changed by 20. So if I had 0 here, I must have had 20 beforehand. All right, going along. What else can that help me with? Well, I found that this has a change of 2 amps, 7 ohms, 14. If it was 20, before that, it had to be 34. And now I know something about this resistor. 50 to 34, it's changing the voltage by 16 volts. Well, 16 volt change, 2 amp current going through it. It must have a resistance of 8 ohms. So there we go. That's the ticket. 8 ohms. So either method works there. All right. Here we got a little bit of a complex circuit. So a table is definitely going to be a good idea to help us with that one, as well as looking at what's happening here. So we start with some potential. Looks like we got 2 resistors in parallel. Then it goes back through this last resistor here. So 0, 5.7 in this whole spot because we have no resistors to change it. And this current of 0.6 amps is going through this unbroken loop here, and it's splitting into 2 mini currents. So we'll draw the table. I'm going to pause here so you have to watch me draw it. You can pause it and then draw and then start again. All right, so here's my table filled out with just my given information. So I added the 2 resistors I knew, I added what I knew about the battery, and I added that this 5 ohm resistor is getting 6 amps, because if I follow this line back around, it doesn't split at all, so this 5 ohm has that 6 amps going through it. You could also answer this question by doing some equivalent resistance stuff, but that would be a little bit more mathematically complicated. So I say, okay, here's my table. Anything I can figure out? Well, yeah, I know these 2 things. So I can find the delta V. 5 times 0.6 is 3 volts. So that's my delta V for my resistor number 3. So I say, okay, resistor number 3 here, delta V 3 volts, 0 on this side. That means 3 volts on the other side. Great. How does that help me? Well, I just added a voltage. So let's look at voltages. 5.73. I now know these changes, 2.7 each, blue to purple. So let's add that. Resistor 1, we know it has, oops, not I, delta V of 2.7. It's taking it from 5.7 to 3. Same deal for these guys. They're in parallel. They have the same change in voltage, definition of parallel. Well, how does that help me? Well, I just added this to my table, so let's see. I know 6 ohms, 2.7 volts. I can find this current. It's going to be whatever 2.7 over 6 is, using Ohm's law. Because remember, Ohm's law, delta V equals I times R. So that gives us a current of 0.45 amps. So I added something here. Let's go throw it on here. That's the current through the 6 ohm resistor. So this 6 ohm resistor has 0.45 amps. How does that help me? Well, we just wrote a current, so let's think about current. We got 0.6 going through here. It's splitting up. 0.45 is going this way, and then some amount is going that way. How much? Well, current needs to be conserved. So I need to have 0.15 amps go down this branch. 0.6 divides up. If you add these together, you'll get back to 0.6. So let's follow that along. 0.15 is going down, and it's going through my unknown resistor. So for my unknown resistor, I can say it has 0.15 amps of current. Well, I know it's changing the voltage by 2.7. As this current, I can figure out 2.7 divided by 0.15. That'll tell me I need a resistance of 18 ohms to make that happen. Great. Next. It's a 200 volt battery, in case you couldn't read the handwriting there. I'm just gonna do this because I know it might be helpful. So battery gives it 200 volts, hits this resistor. That resistor changes the potential, takes away some, who knows how much. Hits these other resistors. One brings it all the way back to 0. The other one, not quite. So I would need another color in there. All right. And I know we got this current of 4 amps. Let's just draw it. It's going around here. Then we have it splitting. Let's make a table. All right, so here's my table. I've added the 3 resistors I knew about. I knew about the battery's potential, and I had this 4 amp current that's going through the battery and through the 10 ohm resistor. So I've added those as well. Looking at my options here, well, I know resistance and current through this first resistor. It's going to have a delta V of 40 volts. So let's go to our table. Let's put some voltages here. Battery adds 200 if we say we're starting with 0. And then I just found this is changing it by 40. So 200 losing 40 if we're saying the current's going that way over this resistor goes down to 160 volts. Great. Okay, how does that help? Well, let's see, we just added this voltage. I know purple, I know red. This 50 ohm resistor is changing the voltage from 160 to 0. So that's a change of 160 volts. I can't do this one because I have no idea what that is yet. I know these two together give 160, so I could maybe do something with that, but I see here I had this 160, I've got this 50, I can find this current delta V equals IR, so we got 160 divided by 50, 3.2 amps. So let's throw that on our diagram. That's the current going through here. Nice thing about doing this virtually is I can write over things and you can still read it. How does that help? Well, we just added a current. So is there anything new we can learn about currents? We got 4 amps going around, splitting into 3.2. Well, that means this branch must be 4 minus 3.2 is 0.8 amps. So that when they come back together, down here, I get back to my 4 amps. Great. Well, let's follow that along. 0.8 is going through the 137 and through the unknown resistor. So 0.8 amps and 0.8 amps. Well, I can get a delta V here, 0.8 times 137, 109.6 volts. All right, that's a voltage. Let's go back to our circuit here. That's the change in voltage of the 137. So I'm at 160, I'm getting rid of 109.6. That's gonna be what, 50.4 at this green area. 50.4 volts, yeah, 50.4, 109, 159, and then yeah, we get that last little bit. Nice. So, well, that tells me this. 50.4 to 0. My unknown resistor. 50.4 volts. So we can see here, these two together, oops. These two together do just as much as this one, because this is a parallel path to this one overall. So 50.4.8, I can find the resistance. 50.4 divided by 0.8 is 63 ohms. Great. Oh boy, this keeps going. All right, we've got battery. Ooh, I flipped which way the battery was going. Real tricksy there. These guys. We've got that and that. Now I'm looking for this unknown resistor. And so that's all I care about. So it's a good idea. I'm like, I just care about this. I don't care about what's happening with these, so I'm going to make my life easier. I'm just going to stick these two resistors together right away to make the circuit more simple, to help me find this R. I can do the same idea down here. I see these are in parallel. I'm just going to shove those together and help myself out real quick. Notice we couldn't do that in this previous question. None of these known resistors were in series or parallel with each other. Same deal with this one. We could have started this one by just putting these two together as well, I guess. All right, so let's convert this before making a table. So these guys, let's label, let's call this 1, 2, 3, 4. So 1 over the combination of 1 and 2 equals 1 over 50 plus 1 over 50. You do the math out on that, you get that it ends up being half, 25 ohms, and we know that two identical resistors in parallel, the equivalent resistance is like I had one with half the resistance. Because it's like I'm taking the 50 ohms and I'm adding an identical new path, I get twice as much current, so half the resistance. We still have our unknown dude, R, and then 1 over our combination of 3 and 4 is 1 over 3, 1 over 36, plus 1 over 4 is 24. Let's see, common denominator here. I could just look for some common factors here. These are both divisible by 12. This is 3 times 12. This is 2 times 12. So if I multiply this one by 2 and this one by 3, I should get the same thing. Because this is 3 times 12. This is 2 times 12. So to get the same denominator, this one needs multiply by 2, this one by 3. So 2 times 2, 3 times 3. And now 2 times 3 times 12, 2 times 3 times 12. Same denominator. So this equals 2 plus 3 is 5 over 2 times 3 times 12 is, or I could just say, 2 times this, 72. Then we got to flip it to get our equivalent resistance. That's not a very nice number, 72 fifths. We'll write that as a decimal for 72 divided by 5, 14.4 ohms. All right, so that's what happens when I shove those two together, 14.4 ohms. Nice. So let's color that. Because these were parallel things, we still have all the colors of the rainbow here in terms of different potentials. 0. What's the battery? 110. We could also now combine these because they got these things between each other that feels a little weird to do. You could do it if you wanted, but we'll just leave it for now. We'll draw the table with what we've got here. Alrighty, so I've got my table. I've got my 25 ohms, my 14 ohms, and my battery down here. Battery is a 110 volt battery. And I realized they tell me the current coming out of the battery right here, 2.2 amps. So I've added that as well. And let's draw that current, see what it's doing in our new circuit here. Well, whoa, that's cool. That was accidental. I didn't know I could do that, but we'll go with that. Perfect circle. Current going through here is 2.2 amps. No, not my perfect circle. 2.2 amps. And you'll notice it's much nicer than, and this is why we combine these, because here we had 2.2 splitting up down each of these, coming back together. So here we actually knew this was 2.2 again without having to combine anything, and then splitting up again and coming back together again. So by combining these resistors, we stopped ourselves from having to figure out exactly what these currents are, how they're splitting, and all that. Because now we can just say, oh, together they have a current of 2.2 going through them. Overall, these two add up their currents. It's like a 2.2 amp current going through a 14.4 ohm resistor. All right, so I'm going to add that current to my table because they're all getting it now that everything is in series, including my unknown resistor here. All right, 2.2 amps, amps, amps. Mr. Horsley will turn over in his sleep if he knows I'm not putting units on things here. All right, no two things. I know R, I know I. 25 times 2.2. That's 25 times 2 is 50. So this is 55 volts. 14.4 times 2.2. That one we're going to put into a calculator. 14.4 times 2.2. 31.68. Sure. Volts. So this one here is changing it from 0. It took current's going this way. So it had to take away 55 if I ended up with 0 on the other side. All right, this one had 110. It took away 31.68 from that. That's some atrocious math there. 110 minus 31.68. 78.32. Why not? 78.32. All right. So I'm going from 78.32 volts down to 55. So that's a change of 78.32 minus 55. 23.32. 23.32 volts. All right, I know the volts, I know the amps. 23.32 divided by 2.2 amps requires a resistance of 10.6 ohms. All right. Cool beans. Another way I could have done this once I had this circuit like this, I could have said 110 volts, 2.2 amps, 110 divided by 2.2. My resistance has to be 50 overall. So if I have 25 and 14.4, that's 39.4. I need 10.6 to get to total resistance of 50. So could have done it that way as well. All right, last one. Nice. Looking for the potential difference of the battery. So I'm looking for this V. So the light bulb gets a power. This one's the light bulb. It's got the light bulb symbol, sort of 60 watts. So R3, our light bulb, has 60 watts of power. Let's add that to our diagram there. Okay, we want to make that happen with a certain battery. So this battery is going to add some amount of potential going from one side to the other. It's going to hit these resistors. It's going to change it to something before it hits the light bulb. And then these are the same here. All right. Looks like a great opportunity for a table. Let's do that. And we're going to include power in our table this time because we have a power. All right, we got a real Sudoku going on here. I know all the resistors. Don't know the battery, anything about that. I don't know any currents, but I'm told 60 watts going through this resistor. Great. So how does that help me? Well, we haven't needed it yet, but let's write our power relationship. P equals I delta V, or if it's a resistor, I squared R. Great. So hey, I know two things in this row. That means I can find the other things. I know resistance and power, so I'm going to use my power formula. And I can put in 60, 15. So 60 divided by 15, that's 4. And then that's I squared, so the square root of 4 is 2 amps. You're welcome for the nice, easy math. I guess I should say you're welcome to myself, so I can do easy math on the solutions. All right, great. So 2 amps. Well, now, hey, I can find delta V. 15 ohms, 2 amps, 30 volts, 13 ohms, sorry. 2 amps, 30 volts. I could have done that either using the power relationship with the current and the power, or I could have done it with Ohm's law, V equals IR, which is easier. I just multiply these two to get the third. All right, so we got a little something there. That's helpful in some way. We know that's changing it by 30, and we also got this current. So let's draw that current. It's going like that. There's one going here, and they're coming together to make, oh, I have these going backwards technically, I guess. All right, so current from the battery splits up down these two paths, back together through that last resistor. So I just found that this current here is 2 amps. I haven't touched this delta V yet, because I don't really know either of these, so not super useful information just yet, but we will be using it shortly. So this 2 amps I can see is going through the light bulb. It's also going through this 30 ohm resistor. So I can add the 2 amps to that one. 30 ohms, 2 amps, delta V of 60. I'm not going to find the powers unless I see it's necessary later. All right, so this one's changing it by 30. This one's changing it by 60. So purple to blue is a change of 90, right? 30 and then 60. So this is 90, which means this is 90 because this is in parallel with these two together. 90, 90. So I can say the delta V over resistor 2, 90 volts. If you were stuck here, if you weren't sure how to see that, some things that you might have tried to do, combining these resistors because they're in series, you could have done that. And the combined resistor here you would find has a delta V of 90, which then looking at these in parallel, you know, your drawing would now be just something like this, where this is 45. And you would have seen, okay, this is changing 90, this is changing 90, both going purple to blue. Okay, so how does that help? Well, 90 volts, resistance 22.5, 90 divided by 22.5, 4. Great, 4 amps. We sort of see that. We said together they're 45, this one's 22.5. That's half the resistance, so it needs twice the current. That's kind of cool. All right, so let's add that to our diagram. 4 amps going up this path. All right, 4 amps, 2 amps coming together to make 6 amps. Or you can say 6 amps coming in and splitting to make 4 and 2. So that tells me the current through my final resistor here, R1, 6 amps. Also the current through the battery. I guess in an alternate world, we could have solved this using powers as well. Yeah. 35 ohms, 6 amps. 35 times 6, 210 delta V. All right, and that's for resistor 1. And we can finally write some voltages on here. 0 volts. Just got that this was 210 volts. So changing from 0, that means this is 210. And we said going over here is 90 either way, no matter what path I take. So 210 plus 90 is 300 volts. And hey, now we can figure out the battery. Battery is going from 0 to 300. So 300 volt battery. Adds 300, takes away 90, takes away 210 back to 0. So that is our answer. Find the power. Okay, yeah. All right, since we made the table, that's pretty easy. We're just going to multiply power is delta V times I, so 6 times 210, and so on. Let's pause and fill it out. All right, so I've just multiplied across to find the powers, and it says to check your result with conservation of energy. So the battery is adding this much power. It's that many joules every second. The resistors are taking away this many joules every second. Let's see if that works out. 1260 plus 360 is 1620. 1620 plus 60 is 1680. 1680 plus 120. 17 plus 100 is 1800. great. Energy was conserved. Our math worked out, so you can do that for any problem. And all of these problems, I could have done the power column and used that to check that I did everything correctly, because that's an easy check. I know everything in the power column has to add up to the power of the battery. All right. Peace.